All right, gang, next video. Sorry about that previous video. It dawned on me that for a group of students who probably has not seen linear discriminant function analysis um, or discriminant function analysis, that probably wasn't a fair expectation. So I may cover that in 6620. I'm not sure yet because I'm restructuring 6610 and 6620 as we speak. So let's forget that stuff until we learn more about it. I will say just to keep it simple that describing the proportion of variance in each discriminant function, function 1, function 2, and examining the difference in these scores if one is positive, one is negative. It tells us something. If one's negative, the other's negative, and one positive, one other's positive. We don't get much differentiation. So I think that part is reasonable to conclude, even without having discriminant function analysis. In terms of the plot, whatever. I probably shouldn't have covered that, but all right. Okay, let's move into the assumptions, things that we should be able to relate to. All right, so the first assumption that I'm going to test is the univariate, I almost said univariate, multivariate, the univariate normality. And I run it using Shapiro test. And I noticed that right here for Professor B, Unit 2, that we are statistically observe statistical significance at the 0.05 level. So therefore, because of that one line, we cannot assume univariate normality. However, we can go ahead and check multivariate normality, which in my opinion, in the context of MANOVA, is most important. So I try to load the MV normal test. For some reason, the version I had installed wasn't reading, so I had to install it again. And then you can see I came down and accessed the library. And then to access the Martius test, we enter this command. Now, for this assumption to be met, we need both of these p-values, 0.131 in this case and 0.803 in this case, to be greater than 0.05. So skewness and kurtosis are not significant, so multi-normality is assumed. In my opinion, I would go ahead, if I were writing up these results, I would state that the univariate normality between Professor B in Unit 2 was violated. However, I would proceed with the MANOVA techniques because the multivariate normality can be assumed. Next thing we get into is one of the most important assumptions, in my opinion. It's using Box's M test to assess the homogeneity of variance-covariance matrix. We need the heaplots package, and I noticed that I did not have that installed. So you can see here I installed it, and I access the library. Now, I ran into some major problems here because I was having a bad day. I blame bad days on my kids. They were, well, actually, I just had a bozo moment. Yeah, I often refer to my data as a data frame, and I call it DF. Well, I was on autopilot, not thinking, and you can see I had some problems here. The reason? Because I didn't name my data set data frame. I named it data. So once I corrected that with using data instead of data frame, you can see that I get my box M test, and you can see that we do not have statistical significance. So we can assume that the homogeneity of our variance-covariance matrix structure is met. Next thing I want to look at is I need to look at to see if there are any extreme outliers. So we can check for multivariate outliers. I know we've installed R statics recently. This is apparently hard to spell because I misspelled it. So once I corrected for the spelling using this command, we get all cases false, which means we have no outliers that are of concern, no extreme outliers that are of concern for the MANOVA technique. Next thing I look at is the linearity assumption. So we need linearity of Unit 1 and Unit 2 over our professors. So I installed the package Grid Extra, and for some reason I couldn't get these plots to work. Although I think they would have been, it would have been really nice. So what I did is I went back to an old buddy of mine, ggplot2. I installed it, and I ran this command right here, and let me show you what happens there. The ggplot2, yeah, this one right here. So what happens here, if it'll load, is we have all the plots on one graph, which is a little confusing. So what I have to do, if you have ADHD, it's going to drive you crazy. But what I have to do, first of all, is just try to focus on the green dots. It's fit a linear model, but it doesn't necessarily mean the relationship is linear. So when I look at the green dots, it does assume we have pretty close to linearity. When I look at the blue lots or blue dots, it does assume we have something pretty close to linearity. And when I look at the red dots, again, it assumes we have something close to linearity, even though the slope appears to be 0. Do we have linearity? It's suspicious, and again, I write here, important, the slopes don't need to be equal, as they do in within COVA. They just need to be linear. So again, it seems to be questionable to me, specifically for the green and red relations. I forget which professors it's aligned with. So we are probably, what happens when we don't have linearity is we lose statistical power. So we are very likely losing statistical power for our test. Multicollinearity, remember, that's assessed by just looking at the correlation between the dependent variables. We have an extremely low 0.059 correlation, so we're only concerned with multicollinearity if this correlation is above 0.90. So we have no concern with multicollinearity. Keep in mind, if we have multiple more than 2 dependent variables, then we have to compare these pairwise. So just as an example, if we had 3, we'd have to compare dv1 with dv2, dv1 with dv3, and so on. So that's about it. So I am going to in the next video show you how I would write this up, and we will be done with the MANOVA part. All right, take care.